13.4, the integrated rate law, the dependence of concentration on time. So we just looked at how there's a relationship between the rate of a reaction and the concentration of a reactant. The integrated rate law gives us a relationship between concentration and time. And this is useful because it allows us to predict what the concentration of a reactant will be at some point in the future. So maybe you have some toxic waste and you know what the rate of decomposition of it is, you know how much you started with, then you can predict how much is going to be left in 500 years or something like that.
So it can be applied to like the half-life?
It is going to be related to half-life, yes. And this integrated rate law, just like the other rate laws, is going to depend on the order of the reaction. So we're going to look at 3 different situations. We're going to go back to our simple little decomposition reaction. A is decomposing to form products. And so we learned that for a first order, the rate equals the rate constant times the concentration of that reactant. We also know that the rate of a reaction is equal to the negative change in the reactant concentration divided by the change in time. That's what we talked about on Monday night. Just like a rate of speed is the change in distance divided by the change in time. Here we have the change in the concentration divided by the change in time. The negative sign is because we're talking about a reactant. The reactant concentration is decreasing, and the rate of speed it's not speed. The rate of the reaction has to be positive. Because really, can you have a negative rate of speed? Ooh, I was going negative 45 in my car. Well, you were going backwards is all, right? It depends on your point of reference. And, oh, shoot.
Like you were saying, you can't go backwards in time.
You can't go backwards in time. And so we put that minus in there so that the rates end up being positive. So we know these two things, the rate is equal to this, the rate is equal to that, then those two things must be equal, right? So negative delta A over delta T must equal K times A. And that's how we get the T in here. This is called the differential rate law. And then, through the magic of calculus, we integrate the rate law. How many of you guys have taken calculus? Awesome. Awesome. We're, as far as I know, we're not going to actually have to do any calculus. But it's helpful to have had it so that you at least know what I'm talking about when I say integrated, right? So we take this, that differential equation, and we integrate it. And I think it was question 112 at the end of the chapter actually shows the steps in how they do it. But you end up with this, which is called the integrated rate law. So the log of the concentration at some time t, the natural log, is equal to the negative of the rate constant times that time t plus the natural log of the initial concentration of A. It can also be shown in this form. If we graph this, well, let's look at this first. This takes the form of the equation for a line. Y equals mx plus b. So if we graph y being the natural log of the concentration versus time, time is going to be x. So here we have the natural log of the concentration versus time. We're going to get a straight line, and the slope is equal to minus k. The intercept is equal to the natural log of the initial concentration. We'll let all that sink in for a minute. Yes, in the general form, we talk about x and y, right? And this is the y-axis, and this is the x-axis. Yeah. Oops. I'll make that come back? What did I do? I'll just rewrite it, yeah. I don't know what happened. I touched something I shouldn't have touched. So this is what we're graphing on the y-axis. This is what we're graphing on the x-axis. Then this is equal to the slope, that's m, and this is the y-intercept. The slope of this line is negative, but the rate constant is positive. There's a negative in there, right? Negative k is the slope. Questions? It's clear as mud, right? Let's see what we can do with this. We can take reaction data and graph the data to find out what the rate constant and the initial concentration, well, we're looking for the rate constant, really. So consider. That doesn't even look like determine. Consider the equation for the decomposition of SO2Cl2. So this is a nice simple decomposition. We've got one reactant. It's decomposing to form two products. So they're monitoring the concentration of SOCl2 at a fixed temperature as a function of time. And so they're giving us this table. So here's time 0 and 100 seconds and 200 seconds. And they're measuring the concentration of the reactant at each of these times. Okay? What they're asking us to do is show that the reaction is first order and determine the rate constant. Well, how did we figure out what the order was in the previous examples? We needed the rates, right? We looked at the concentration and the rate. We don't have the rate measured here. Could you figure out the rate from this table? You could. You could. You could take the change in concentration divided by the change in time, right? And that would give you the average rate for that time period, right? But here we're going to use graphing instead. So if this is a first order reaction, pointing in the wrong place, if this is a first order reaction, then we should be able to use that integrated rate law that we just used. So let's see what happens when we graph the data. We're going to graph the natural log of the reactant concentration versus time. And when we do that, sure enough, we get a straight line. That shows us that the reaction order is first order, because this is what a first order reaction does. You can do this by putting points into your calculator. The graphing calculator will actually show you the graph, but even a simple scientific calculator will allow you to put points in and do linear regression and come up with the equation for a line. And so that's how they came up with this equation for the line. Or you can use something like Excel and plug this in, and it'll do that calculation for you. So here's our equation. The slope is equal to what? Negative k. So it was the natural log of, forgot what my reactant was, is minus kt plus the natural log of the concentration. Oh, I reverted. Okay. SO2, Cl2 at time 0, and this is at time t. The slope is minus k. So the rate constant is, here's the slope, negative 0.00290. It's going to be positive 0.00, no, need one more 0, 290. What are the units on the rate constant? Per second. Any questions? Scientists like to graph data. You get a lot of information, and it kind of smooths out some of the random errors. Because this data is drop-dead gorgeous data. All those points are like right on that line because they made it up, right? In a real situation, you'd have a little more variation. But taking all this data together and doing linear regression on it gives you a much better result for your rate constant than looking at individual chunks of it. So then let's use this graph and predict the concentration of that reactant at 1900 seconds. So let's just remind ourselves of the equation. Um, 0.000290 times T minus 2.30. So we want to know this concentration at time t. Time t is 1900 seconds. What do we have to do? We just have to put 1900 in for t. That's all we have to do. This equals 1900 seconds. So 0.000290, change the sign, times 1900 minus 2.3. So I'm getting negative 2.851. Is that the concentration of SO2Cl2 at 1900? What's the big tip-off that that can't be a concentration? It's negative. You can't have a negative concentration. Well, that's not the concentration. That's the natural log of the concentration. Okay? So to get the actual concentration, we need to do the opposite of the natural log, e to the x. So it's e to the 2.851. You're missing the stuff on the bottom. I'll try not to write on the bottom in the future. So SO2, it will be on YouTube later, and you will probably have an unobstructed view. But I will take that into consideration. 0.0. How many sig figs should I put on this? How many was on the original data? 3? Then we should probably go with 3. 578. And what's the units on that? Molarity. Okay? Yes?
On the last bit, what happened to the 2.30? Did you just take the natural log of it and put it on the last line?
What happened to the 2.30? That's good. Good question. I took negative 0.000290 times this 1900, and then I subtracted 2.30, and I got this number.
No, but on the last line.
On the last slide.
Yeah.
Oh, you used 2.30 because it's the y-intercept.
Yeah, you just had the.
Did I forget something?
You just had the negative 0.000290 seconds.
Oh,
Yeah, that's what I was thinking.
okay. That's an excellent question. The slope is the rate constant. The 2.3 is the natural log of the initial concentration.
Oh.
Okay?
Yeah.
But good question. Any other questions? No, I'm lost. Okay, we did that one. Okay. determine the concentration of a reactant at a given time. So cyclopropane rearranges to form propene in the gas phase. How lovely for it. The reaction is first order in cyclopropane and has a measured rate constant of 3.36 times 10 to the minus 5 per second at 720 Kelvin. If the initial cyclopropane concentration is 0.0445 molar, what will the cyclopropane concentration be after 235.0 minutes? Doesn't this sound fun? Yeah, it's awesome. Now, most people are going to look at a problem like this and go, some of that sounds a little familiar, but I'm not really sure what to do with it. A good strategy is to just start picking things out. Usually the numbers are important. Let's pick the numbers out and write down what they are. So we've got this 3.36 times 10 to the minus 5 per second. What is that? It says in the problem. The rate constant. Okay, so that's K. We call the rate constant K. 720 Kelvin. Have we done anything with temperature yet? No. Do you think that's going to figure into the calculation? No, it's not. They just kind of threw that in there. If you go ahead and write down that the temperature is 720 K, it's not going to hurt anything. But that's one of those extra pieces of information. So then we have 0.0445 molar. That is the initial concentration. Okay, so I don't have a great abbreviation for cyclopropane, so let's just call it A. So this is the concentration of our reactant at time 0, the initial, right? And then what will the concentration be after 235.0 minutes? That is time. 235.0 minutes. Always write units. Always. So we're trying to find the concentration of A at time t, right? That's what we're trying to find. This is our question mark. What is that? This is a first order reaction, and we just learned about the integrated rate law, right? It looks to me like we have most of the pieces we need to use the integrated rate law. So the integrated rate law was the natural log of A at time t is equal to minus kt plus the natural log of the initial concentration. Do we know what K is?
Yes.
Yeah. Do we know what T is?
Yes.
Yep. Do we know what A0 is? Yeah. And we're trying to find out what this one is. So all we need to do is put the numbers in there and solve for A at T.
Negative KT?
Negative KT. So negative, and K is going to be 3.36 times 10 to the minus 5 per second. Should I put 235 minutes in there? The units aren't going to work out, are they? We need to change that into seconds times 60 seconds per minute. Can somebody tell me what that is? 14,100? That's a big number. So I'm going to just bend around the corner here because, well, I ran out of space. So there's the T, and then the natural log of the initial concentration, which is 0.0445 molar. Sorry about that. You like that? I promise I won't turn it all the way around. So then what I'm going to do, it kind of depends on how your calculator thinks. I'm going to kind of start at the end, 0.0445. I'm going to take the natural log of that. And then I'm going to add 14100 times 3.36 EE minus 5. Oh, I forgot to change the sign before I did that. Start over. I'm going to start over. And I'm going to stop talking too. Natural log. Okay. Okay, so I came up with this being this really weird looking number. Did anybody else get that? Get minus 43886.5? No? I'm not surprised. That sounds much nicer. I'm going to try this again. Times 14100 equals plus 0.0445 natural log equals. Yeah. So I think I mentioned this earlier. Especially on a complicated calculation, do it twice. The second time I did it, I'm coming up with the answer that he got, minus 3.586. And since he already got that, we're going to call that best 2 out of 3. Is that our answer? No. That is the natural log of A at t. So we need to do the anti-log of both sides. A of t equals e to the negative 3.586.
Negative, positive.
0.0277 molar. Question?
Can we just, for the equation, can we just introduce the e first and just get rid of all the natural logs before we start? Or
No, because we've got negative kt plus the natural log. Yeah.
well, that would be.
It doesn't break the math rules though.
It wouldn't be. We'd have to do like e to the negative kt times a. Yeah, I mean, good.
I have something to show you about that, but does anybody have any questions about what's up on the screen right now? Yes?
I'm not sure if I just calculated it wrong, but my A of t is the same as the A initial.
This isn't quite right. I'm getting minus 3.586. So let's jump back here a little bit. You see this guy? You could use that guy if you want to. I'm not sure if that would help or not, but that's an option. Just be, when you're rearranging things that involve logarithms, just be careful. Okay, second order. We can get these integrated rate laws using the same idea. Here the rate is k times the concentration squared. The rate is still the change in A over the change in time, the negative. And so we get this is our differential rate law. That doesn't really help us very much, but we take that and we integrate it. And we also come up with an equation that's in the form of an equation for a line. Sorry, I'm having an argument with the internet. Y equals mx plus b. So now what we want to do is we want to graph 1 over the concentration for the y-axis versus time, and that will give us a straight line where the slope is k and the y-intercept is 1 over the initial concentration. You can either go through the calculus yourself, or you can believe me. Some people want to go through it themselves and prove it to themselves, and I encourage you to do that. Or you can just believe me. Any questions? Scientists love things that end up being straight line plots, right? They're really easy to find an equation for, and you've got linear regression. You can get a regression constant and figure out how well your data is fitting the equation, and it's just really nice. So let's look at an example for the second order. Here's a decomposition of nitrogen dioxide. And they're monitoring the reactant concentration at a fixed temperature as a function of time, and the data is tabulated over here. And they're asking us to show by graphical analysis that the reaction is not first order, but that it is in fact second order, and also asking us to find the rate constant. So how would you do this? You would take this data and you would graph it. Now this is where being actually able to see the graph either on your calculator or your computer screen would be helpful. Not absolutely necessary, but helpful. So this is what happens if we use the first order graph. Natural log of the concentration versus time. If it's first order, this should be linear. Well, there's the best line that can be drawn through those points. Do those points match up well with the line? No. If you're doing some wishful thinking, you might say, well, yeah, they're pretty close. They're just kind of off at both ends and in the middle. Yeah, well, that means it's not. See, this is a curve, right? It's a curve. It's not a line. It's not first order because it's not linear. Messy data that's linear is going to be scattered on both sides of the line all over the place, not below the line in the middle and above the line on both ends. So if we do the second order graph and do 1 over the concentration versus time, then we do get a beautiful straight line. This demonstrates that the reaction is second order. It depends on the square of the concentration. The equation for the line is y equals 0.255x plus 100. Now they were asking us to find, I forgot, the rate constant. What's the rate constant? It's the slope of the line, 0.255. What are the units? If you were just looking at a graph like this and you were trying to determine the slope just looking at the graph, slope is rise over run, right? The rise, the difference in the difference in y, divided by the difference in x. What are the units on the y-axis? 1 over molarity. What are the units on the x-axis? Seconds. So that gives us m to the minus 1, s to the minus 1. Questions? So using the graph and this best fitting line, predict the concentration at 2,000 seconds. See, this experiment was done over the course of 1,000 seconds, right? And we got this nice line and a nice equation, so we don't actually have to continue the experiment for another 1,000 to out to 2,000 seconds to find out what the concentration is. We can just use the equation to figure it out. So what does y represent? This y. It's 1 over the concentration. One over the concentration equals 0.255 and the units of that were per mole per second times the number of seconds, right? 2,000 seconds plus 100. That's the y-intercept. What's the units on the y-intercept? 1 over molarity. So when I multiply these two numbers, what unit do I get? Let's do it this way instead. What happens with these units? Per mole per second times second. The seconds cancel out, right? And this ends up being per mole, and we're adding it to per mole, and so we're good. 0.255 times 2,000 plus 100 equals 610 per molar. Is that the answer?
Nope.
No, we have to invert it. It's 1 over the answer. So use that little 1 over x button on your calculator, and we get the concentration is going to be 1.64. You don't like that number? 1.64 times 10 to the negative third. And that fixes the unit too. Inverts that as well. Questions? What about zero order? We're going to do the same thing. The rate equals K. Again, the rate is negative. The change in the reactant concentration divided by the change in time. And so we get negative delta A over delta T equals K. We integrate that, and we end up with the concentration is equal to minus KT plus the initial concentration. Again, a nice linear equation. So here we've got A at time t versus time, and the slope ends up being minus k. So this one is even simpler. No logarithms, no 1 over anything. So of course you could solve very similar problems using this integrated rate log. Any questions? Half-life. The half-life is abbreviated T1/2. It's the time needed for the concentration of the reactant to drop to half of what it started at. So it's the time for it to go to half. If you took Chem 3A, we talked about nuclear chemistry a little bit, and you talk about the half-life of nuclear isotopes. So if we look at something with an initial concentration of 0.5 molar, and if the half-life is 50 seconds, that means after 50 seconds, the initial concentration is cut in half. So what will the concentration be after 50 seconds? It'll be 0.25 molar. It'll be 0.50 divided by 2. So 0.25 molar after 50 seconds. What about after 100 seconds? It'll be cut in half again. So we take this one, we're going another half-life, so it gets cut in half again, and then we get 0.125 molar. So every half-life, the concentration gets cut in half. The expression, it will reach 0 eventually. Takes a really, really long time. Yeah. The half-life expression, though, is going to be different for each reaction order. There's kind of a theme going on with that. So for a first-order reaction, this isn't the line equation of form of this, it's the other one. But the natural log of the concentration at time t over the concentration initial is equal to minus kT. Well, when t equals the half-life, then we know that the concentration is equal to 1/2 of the initial concentration. so we can plug these things in and solve it and find out what is that half-life. So we've got the natural log. The numerator here is 1/2 of A0, and it's divided by A0. So the natural log of that whole thing is equal to minus K times T1/2. So let's simplify what's inside the parentheses here. A0 over A0 cancels out. And so this is equal to the natural log of 1/2. What's the natural log of 1/2? It's 0.693. So this is equal to 0.693. So then what does T1/2 equal? T1/2 is equal to negative 0.693 divided by the rate constant.
The ln of 1/2 is actually negative.
Oh, thank you. I'm just like, wait a minute. That's just how T1/2 can't be a negative number. Yeah, this is negative, and then this ends up being positive. Thank you. Solve my problem.
There you go.
So T1/2 is 0.693 divided by the rate constant. It does not depend on the initial concentration. First order reaction. So here's the typed out one. T1/2 is 0.693 divided by K. The half-life is independent of the initial concentration. So if we start with 1 molar here, after 1 half-life, we have half molar. After 2 half-lives, we have 0.25. After 3, we have 0.125. And it just cuts in half every time, and it keeps going. Where would it eventually stop? You get down to 2 molecules, right? And then you get 1 molecule, and then that one decomposes.
Works.
There are quarks. But when you have 1 molecule left and it decomposes, there's no more halves. You're done.
So this is an approximation.
I guess you could say that, yes.
So it ends at 1. Or single.
It gets down to a single molecule, and then there's none. And then there was none.
Okay.
So a first order reaction has a half-life of 26.4 seconds. How long does it take for the concentration of the reactant to fall to 1/8 of its initial value? 1/8. So we've been doing all this fancy stuff with math and rearranging equations, and then this is one that you don't really do that with. Well, you start with 1, the whole, right? And after 1 half-life, you have half, and after a second half-life, you have a fourth, and after a third half-life, you have 1/8. How many half-lives? 3. So it's 3 times the half-life, 26.4 seconds. I think it was 78 something. 79, close. 79.2 seconds. That's it. Right? Like, yeah, but we've been doing all this hairy stuff, and now you're just counting and multiplying? That's for a first order reaction. Nuclear reactions where you have radioactive elements decomposing, those are first order reactions, and they follow this very nice pattern. The second order integrated rate law, Here's the form of that. Again, for the half-life, T is equal to T1/2, and then we know the relationship between these two guys. So 1 over, now we're going to sub in 1/2 A0. That's going to equal K T1/2 plus 1 over A0. So what does this guy equal? I don't like fractions in the denominator there. That's 2 over A0, right? And we're trying to get T1/2 by himself. So if we take this guy and move it over here to the other side, then we've got 2 over A0 minus 1 over A0. What does that equal? 1 over A0. And that is equal to K times T1/2. So it follows that T1/2 equals 1 over the rate constant times the initial concentration. For a second order reaction, the half-life depends on the initial concentration. If you have high initial concentration, is your half-life going to be big or small? Somebody commit. Small. Because 1 over a big number is a small number. If the initial concentration is small, then the half-life will be longer. So a lower initial concentration gives a longer half-life. It's inversely proportional to the concentration. And then we can't leave out the 0 order. So 1/2 A0 is equal to minus K T1/2 plus A0. I'm going to take this guy and move it over here because I want to get rid of that negative sign. And then I've got the A0. And to bring this guy over here, I subtract him. And so that equals 1/2 A0. T1/2 equals A0 over 2K. For a 0 order reaction, the half-life also depends on the initial concentration. But now if the initial concentration is large, the half-life is long. And if the initial concentration is small, the half-life is short. So it's an inverse, it's a direct proportion. Half-life gets shorter as the initial concentration decreases. Any questions? I think this is the last slide. This is a summary of all this stuff we talked about tonight. So 0 order, first order, second order, here are the rate law expressions, the units on the rate constant, the integrated rate laws, what the straight line plots look like, and what the half-life expressions are.